Good afternoon, everyone. Welcome to today's webinar, The Power of Direct Current. My name is Katie Zaccardo, and I work with Marketing and Communications at ABB. I will be moderating today's webinar. Before we get started, I wanted to go over a few housekeeping items. All participant audio will be muted during the event. If you would like to ask a question during the event, please use the question box in the GoToWebinar panel. We will try to answer your questions during the event. Today's webinar is being recorded. A link to the recording will be emailed to you following today's event. Feel free to forward the link to people you know who could benefit from the presentation. You may even want to tweet about this on your Twitter account. Before we go into our feature presentation, I wanted to introduce the 2013 ABB Automation and Power World event. This year's event will be held March 25th to 28th at the Orange County Convention Center in Orlando, Florida. Automation and Power World is the premier event for engineers and business leaders, designed so that you can experience and learn the latest in automation and power technology and how it can benefit the profitability of your business. This year's event will be held, as I said, March 25th. This mega event will include over 400 educational workshops on topics that are vital to the success of your business. Today's webinar will give you an example of the type of practical training you'll experience at the event. You can earn PDH and CEU credits and spend some valuable networking time with your peers. The event will also feature a Technology and Solution Center with over 150,000 square feet of exhibits and nearly 100 tons of electrical gear and hundreds of experts ready to answer any of your questions and to share the future of automation and power solutions. We are expecting over 4,000 attendees at this event, making it an excellent opportunity for face-to-face sharing of ideas and a chance to get reacquainted with old friends and colleagues. Here are just some examples of the educational workshops developed for all audiences, roles, industries, and experience levels. Be sure to bring your questions and get them answered by our expert panel of presenters. Here are some comments from past attendees. I'll be back at the end of today's presentation with more information about ABB's Automation and Power World Conference. Now I'd like to introduce today's speakers. John Levins is the ABB North American Business Development Manager for Data Centers and Infrastructure. He has designed, managed, constructed, and commissioned electrical systems in large-scale data centers in the U.S. and Europe. With over 22 years of mission-critical data center, industrial, and healthcare facility design, operation, and maintenance experience, he brings a practical, holistic approach to facility design and a passion for client satisfaction. He holds a Bachelor's of Science in Electrical Engineering from Drexel University. Frank Catapano is the Global Systems and Portfolio Development Manager at ABB's Data Center and Infrastructure Product Group. In addition to his global duties, Frank is responsible for operations, R&D, technical services, and engineering at Validus DC Systems, which was recently acquired by ABB. Frank brings over 30 years of electrical engineering, systems integration, power systems maintenance and testing, manufacturing, and contracting experience to the ABB organization. All right, Don and Frank, I'm going to pass it off to you now.
Well, thank you, Katie. So today we'll be discussing direct current in the data center and why it's relevant. We'll review direct current topologies, design, and TCO points of interest to owners and engineers, as well as the future of DC as ABB sees it. As Katie said, please feel free during this presentation to type any of your questions in the dialog box in the GoToWebinar box to your right. We'll attempt to answer all those questions at the end of today's presentation. So why all the interest in DC? Well, it's complicated yet simple. Each owner-operator has a specific business model that they're hoping to use to differentiate themselves in the marketplace. Some want efficiency and reliability. Others, it's all about renewables or being green. Some want to be part of the long term and optimize their total costs. And then others want a little bit of everything. The reason simply depends. So it's normal to want to investigate and give careful consideration to any and every distribution scheme that's both practical and possible today. And direct current is quickly becoming both. But no discussion of DC would be complete without some historical perspective, a nod to our past. We all know that Tesla, Westinghouse, and Edison differed on how to distribute power back in the day. But at the time and since, power distribution has been predominantly alternating current. But in the 100-plus years since that debate, technology and power electronics have evolved to the point that virtually everything we now touch or use in our lives today, from our cars, trains, smartphones, computers, they all rely on DC power. And even long-distance high-voltage distribution is increasingly using DC as the most efficient means to transport large amounts of power over great distances. Perhaps the most reliable DC system ever installed, the telecom industry. If you haven't converted your home to voice over IP, you know your phone works when all the other power is out everywhere, all due to DC power. So why not look for ways to simplify that distribution and step down from 230 kV to 12 volts DC as fast as practical? A look around the globe and we see that DC is being used or tried virtually everywhere for all sorts of reasons. Many may be familiar with Facebook and their hybrid approach to using a UPS-less AC distribution and a DC battery system fed from AC power to their servers, both on and off grid. Now, this design may not work for everyone, and not everyone certainly has their funding, because one size doesn't fit all. But unless we look at the options and opportunities that are out there, we won't know what works. In Switzerland, ABB helped Green, a local colo and hosting provider, implement a 380-volt DC solution. And they intend to expand their use of DC in their Tier 3 facility. Why? Simply, they believe it fits their corporate mission. And in China and other parts of Asia Pacific, several projects of different DC voltages are installed or currently underway. Back home, DC is increasingly on the news wires, whether it's about the distribution system itself and its merits, or major companies talking about the potential benefits their clients may see. The discussion about DC is here and here to stay. We've even seen standards organizations looking to organize and formulate consensus-based standards to ensure those that design, construct, or operate DC facilities do so based on safe engineering practices and using tested components. And more vendors of networking, storage, and computing platforms are looking to offer direct current power supply support for their products. So then, let's discuss DC and some of the topologies being used today. Frank?
Thank you, John. Good afternoon, everyone. Thank you for participating in today's webinar. I wanted to take a few minutes of today to discuss some of the topologies that we're seeing around the globe with respect to active DC deployments. First, I wanted to review some of the voltages that we see that are associated with those systems. So early on, when DC was first being considered for use in the data centers, there were two different schools out there. One was an Intel EPRI PIAC model that revolved around feeding 380 volts directly to a server. Another was a hybrid system where 575 volt DC was distributed through a building and stepped down to 48 volts at or near the point of load. The intent of that original system was to make 48 volt DC infrastructures scalable based on the increasing power densities that we were seeing in the marketplace. Over time, the industry seems to have coalesced around a number of voltages that seem to be used interchangeably. So today you'll see what's referred to as high voltage DC in the data centers, spoken about in terms of 400 volts DC, 380 volts DC, and or plus or minus 190 volts DC. You'll also see a plus or a minus in front of the 400 or 380, indicating a positively or negatively grounded system, which is vastly different than the plus minus 190 volt DC, which indicates a midpoint grounded system. And the purpose and the interest behind the midpoint grounded system is that the voltage to ground is half that of a 380 or 400 volt system. We also see 240 volt DC systems being deployed predominantly in Asia, in New Zealand. Of course, the industry standard that John spoke about earlier is the 48 volt, which is interchangeably used with 53.7. And we see a number of hybrid systems consisting of 380 volt stepping down to 12 volts. You'll also see 380 stepping down to 48 in some instances. And we've seen a number of 240 volt DC to 12 volt systems. All of them have their place in the industry. It's important to select the right solution for the right problem. But I wanted to review some of the basics, pros and cons associated with these different systems. So that the slide you see before you is really the de facto 48 volt telecommunication system that we all know and love here in the United States. And the system has been proven to be incredibly reliable, and it's reliable for a number of reasons. One is the modular nature of the rectifier chargers. Second is the lack of a secondary conversion phase. The batteries are directly charged off of the rectifier chargers. So it's a very, very simple system to understand and operate. Unfortunately, it just doesn't meet the increasing load densities that we're seeing in the data center, and the system doesn't scale well as a standalone system with loads above 400 kW. Some of the other variations that we see in the industry are a 380 or 400 volt or even 480 volt AC system using very similar modular rectifier chargers that are used in the 48 volt telco system, charging a 240 volt DC link on the left and a 380 volt DC link on the right. Both of these systems are sound technology. You may or may not have rack level conversion. Again, the drawing on the left shows a 240 to 12 volt DC to DC converter. But there are some drawbacks associated with both of these topologies. One being they're not very scalable in the form factor that you see on your screen. They generally cap out at a rating somewhere along the order of 250 to 275 kW. They also have a variable output voltage. So in any of these DC systems, including the 48 volt topology, if you're not regulating the battery bus voltage, you have to oversize all of your branch circuit feeders, your conductors, and increase the number of terminations, which all impact cost, reliability, constructability. They all need to be sized for the maximum current that you would see at the discharge cutoff voltage of the battery string. So in essence, you're building roughly a 28% larger power distribution infrastructure with respect to cabling and so forth to accommodate an event, in our industry, an outage that happens 0.001 or less % of the time. And we don't believe that that's a very good capital investment cost, but it is the way people are constructing these systems. So hopefully today you'll walk away with a better idea of some of the other options that are out in the world. Two such options are a little bit more scalable than the previous slide. The system that you see on the left, we've deployed successfully in many, many instances, utilizes a high-performance bulk rectifier, which feeds a 380 or plus minus 190 volt bus within a switchboard. Off of that switchboard on the lower left-hand side, you'll see we have a standalone battery charger, and the operational sequence of the system is pretty straightforward, and that's part of the beauty of DC. The batteries are diode isolated from the rectifier charger output. If the rectifier output voltage decays below the battery float voltage, the diode goes into conduction. Very simple system, very reliable system. The only challenge one has with it is the bulk rectifier is unfortunately a single point of failure. And again, the system has a variable output voltage on the bus, but highly proven technology. If you were to take that system and make a few tweaks to it, you would get the system that you see on the right-hand side of the slide. This uses power factor corrected or active front-end rectifiers that are modular in nature, with battery interface modules that manage multiple strings of batteries. However, each string is treated as an independent entity in this type of topology. And you'll see an extra conversion phase down here, which is a DC to DC converter. In this system, the bus voltage on the output of the AFE varies when the batteries are discharging. However, the DC to DC converter acts as a buck and allows you to have a constant voltage output on the load side of the system. Number of benefits to having that additional conversion. One is we have a constant voltage system that enables us to build a much smaller infrastructure. Another is we're electronically limiting the battery energy through the DC to DC converter, so issues like high short circuit currents and arc flash that people either don't understand or are afraid of become non-issues in this type of topology. So all of these systems that are modular in nature really go back to and take a lead from, in some way, shape, or form, a 48-volt topology. And, my apologies. I left out the Facebook folks. Sorry about that. One last topology, and John spoke about this earlier, is a hybrid AC-DC system used by many of the participants in OpenCompute.org, which is being championed by Facebook. This topology uses straight AC directly into a rack-mounted PDU, so there's no UPS on the AC side. And then for backup, leveraging dual input PSUs on the servers, we have either a 48 or 380 volt battery system that provides uninterrupted power in the event of an outage. Batteries are generally sized for short run times so that one can just have enough time to start your generator. You can obviously extend the battery run time if you so choose. Back to our friends in the telco world, some tremendous attributes of this system. It's served as the workhorse of the telecommunication industry since we've had phones. Its problem has been it's just not a very scalable system. One of the things we heard when we were doing our market research from many telco customers is, as we ramp up the power ratings of these systems, the structures of our buildings can't support the weight of the copper and the batteries required to enable them to operate successfully. So we believe, however, that, as I said, there's attributes of this that we could take away, that we can scale via voltage and have a highly reliable system. So if you could take a 48-volt telco system and take all the attributes of it, you would get something that would look like this. A medium voltage service entrance transformer with that same modular rectifier array, float charging, in this case, a slightly higher voltage bus, and then using the same style rectifiers, again, modular, scalable. If you'd like N+1 or 2N, you could just simply rack an independently controlled rectifier or DC to DC converter into the array and garner similar levels of reliability from that telco system. The other things this type of topology allows you to do is integrate other sources quite easily. Because each module operates as an independent entity, we could put any other variable DC voltage source directly into a DC to DC converter and parallel its output with an array that's fed from a utility. And there's technically no limit to the number of converters that you can put into this array. You can also extract some flexibility out of the system because we do have the makings of an online double conversion UPS in this topology. So we often hear, what if I have some parasitic type AC loads that I need to power? We could very easily provide an inverter module in this type of system to power AC components throughout the data center. So DC enables us to have a tremendous amount of flexibility in terms of the types of sources that we can integrate, the levels of reliability that we can have within our facilities, and there's really no limits to the engineering topologies that we can deploy. You can also use flywheels on these systems. We've successfully deployed flywheel technology by Vicon on midpoint grounded and 390 volt systems. We've used active power flywheels, which can be configured for DC direct on some of the higher voltage DC systems. So you can go anywhere you'd like to in terms of design by being able to integrate multiple sources, either as primary power and or secondary power. And by having a DC topology, it allows us to take a standard power supply architecture where we have on the front end of a server a 277, 120, or 240 volt rectifier, and simply remove that from the power equation, or from the power delivery stream. And when you remove that component from the server, a number of things inherently happen. One, if you have a constant voltage output in the system, you can use a 380 volt DC power supply that's significantly more efficient than a DC power supply with the variable voltage input window, because you can optimize the components around a very tightly held voltage. The other thing that happens from a reliability point of view is your parts count goes down in the server, so you should in theory have increased reliability. And lastly, you're rejecting less heat in the server, again, something that impacts both efficiency and reliability, not only of the energy used to power the server, but also the energy used to cool development of the equivalent of the old SEBIMA or IDIC power equipment curve. So this is very real. There's a number of regulatory and independent agencies that are coalescing around the standards for DC servers. So DC servers are here to stay, in our opinion. They're very real, and we're seeing a tremendous amount of activity in the industry, both on the server manufacturer side and the customer side. So John, I'm going to turn it back to you.
Thanks, Frank. So why do some people discuss DC and sometimes discuss it as being more reliable than AC? Well, as Frank indicated, it can vary depending upon your needs. Perhaps it's because they see DC systems with fewer switchboards and breakers and other potential points of failure or maintenance. It could be that reliability for them is based on how well trained and prepared operators are to react to a loss of power at perhaps the most inconvenient time, say 3 a.m. on a Sunday before a nor'easter hits the coast. As Frank indicated, heat means lost energy and requires treatment. So the less heat you put into the system, the less heat you have to remove or cool. That may simplify your mechanical system. And by being able to parallel DC, as Frank indicated, you have fewer complicated control systems by not needing to synchronize those multiple sources. Perhaps another issue might be power quality and harmonics, where if you were able to reduce the number or the size of VFDs or possibly implement DC motors in your system to alleviate the need for harmonic correction or dampening, this could be conceived or thought of as a reliability improvement. So today we see designs as well that have fault currents in the 100 to 150 and 200 KAIC range. So if it's possible to lower those levels, you could be better assured that your overcurrent protective devices are going to open and safely clear any fault condition and not risk opening catastrophically. A grid-to-chip design, as it's often called, can offer an owner benefits. For example, an IEEE 519 compliant design would mean no harmonics or filters to degrade the efficiency in the system. And the utility would potentially see no reactive power entering their system. At the data center side, you could potentially simplify your multi-source AC design. And rather than having perhaps a complicated and expensive parallel generator system, you could look to implement a simple distributed generator system. The DC bus, as Frank mentioned earlier, allows us to parallel multiple DC sources and for them to be connected simultaneously. And using droop compensation, we can power that critical load depending upon which source is strongest at the time. And less complex controls, as we mentioned, really do allow and make it easier for operations to manage the systems. And as some manufacturers have noted, and Frank indicated earlier, if you can make your IT platform more efficient by deleting or improving that input power transformation and accepting native DC, well, that could be a benefit as well. Yep, today's data centers, total cost of ownership boils down to energy costs, reliability, and spatial constraints, and is often a tug-of-war between CapEx and OpEx. If efficiency means a smaller electric room footprint for some, this may mean a smaller build-out, reducing their CapEx expenditures, but often building and land costs tend to be the least costly items in a modern large data center. So perhaps they're more concerned about the ability to scale in a reliable, consistent manner. That may be of greater importance. I mean, being able to deploy only what you need when you need it to match that customer demand with your capacity and meet reliability needs while delivering on a specific service level agreement, these are often significant factors in any design. Today, while mostly outside the U.S., there's also discussion and consideration to alternative energy credits, such as carbon offsets, or as Frank indicated earlier in his slide, the use of solar power. Yep, today's data centers are much more complex than they are, and there's many factors to weigh in the overall design process for all parties. But looking ahead, ABB believes the future for data centers involves smart grids that are fully implemented at the utility level, and it can be exploited by the data center operator to convert any spare capacity they may have from a cost to an asset. For example, today's data centers typically lock in their energy costs based upon the amount of energy that they project to need. And so their rates, their tariffs are based upon what the utility has put into their infrastructure investment and what they're hoping to get back in terms of their billables. Well, data centers today aren't able to run their diesel gensets to peak shave or reduce any of their base load, often due to simply environmental regulations prohibiting the use of diesel gensets. But in the future, if there are fuel cells deployed and large solar panel arrays are connected directly to a data center and connected directly to the DC side of that distribution, perhaps you can offset that base load. And while there may be times during your typical compute day where there'll be lower demand, but you'll have greater on-site generation capacity, you'd want to be able to transfer that excess capacity back to the utility via a smart grid. So marrying that microgrid structure on your property and that utility smart grid off your property is going to allow the data center owner to sell back that power and basically turn their enterprise, their power consumption into an asset. Tomorrow's data centers are really going to be more agile and flexible than they are even today when it comes to power. DC in the data center today is actually exiting the early adopter phase, and we're seeing more projects being proposed and developed globally. New projects that are based on consensus standards, New projects that seek to implement a DC microgrid either now or plan to take advantage of such and alternative sources in the future. In essence, the data center can benefit from the power of DC today. And that's going to conclude our presentation for today. So let's see if we have any questions. Frank, do we have any questions?
We have a number of good questions, John. Thank you. One of the first questions that came in this afternoon was, how are short circuit currents reduced? And I want to make clear that short circuit currents in many of the systems that are reviewed can in fact be a problem. One of the topologies that we're fully supportive of here at ABB is one that includes an output DC to DC converter. And the way those converters work is there's very sophisticated electronics that monitor the rise time of the current. So under a short circuit condition, obviously current starts to go very high. When you have a very high sampling rate, you can, in essence, intercept and shut down power to a short circuit current, or even pulse current to a load to clear a fault if you have the right control system. So we use a secondary DC to DC output converter in that very manner. So you're limiting the energy that the batteries can deliver because you have an additional electronically controlled piece of equipment in the power delivery stream.
Thanks, Frank. We have another question here. Perhaps you want to talk about, and that is what manufacturers are making or supporting 380-volt DC products today, such as servers and networking products?
Sure. If that was meant for me, we have a number of partners that we've publicly demonstrated, and not to be nebulous, but we are under NDA with a number of the power supply folks who don't or are not yet quite ready to announce. But we've seen commercial server and network switches provided in demonstrations that we've done from a company called NEI outside of Boston. Hewlett-Packard has been hugely supportive of providing DC equipment in a number of facilities that ABB has touched. We have partners such as Avnet, very, very large international service and product provider that's looking at this. We've been running equipment from IBM, particularly their mainframes, successfully for many, many years on both 575 or 400 volt or 380 volt topologies. Our Syracuse University project has a number of IBM mainframes that have been running for going on 3 years now at 380 volt. Delta out of Asia not only has a DC power supply system, but they also make power supply units for servers. And based on the activity that we've seen, one of the other questions that popped up here is how do you retrofit existing servers to accept direct current? And that's an interesting question. It turns out, and many people don't always see this point, that the server is agnostic to the power supply that you put into it. So the servers don't actually change. It's the power supply unit that you put into the slot or the silver box that powers the server that actually changes. So as long as if you had an existing server and wanted to make that type of change and you had a replaceable power supply, you could in theory pull out your AC power supply and plug your DC power supply in, and the server should work just fine. We advocate really looking at, again, with the focus on the hyperscale data center and large user side of the equation, we tend to look at bulk replacements or migrations of servers. So we would really recommend looking at a 500 kW or 1 megawatt type of load. And as with any technology refresh, you usually take a good portion of your data center either out of commission or build it somewhere else and migrate over. So I don't personally think it would necessarily be practical to retrofit servers that are existing in a rack. You'd have to replace the power strips, the power cords, and the power feeders. So you're well on your way into a major infrastructure project when you go that route. So integrating DC as a part of a technology refresh may in fact be a more cost-effective methodology to approach such a project with.
Yeah, and that goes along with another question we've been asked in the past, which is, have there been any DC retrofits done to existing data centers? And the fact of the matter is, as Frank just indicated, it would be very difficult to basically go into an existing AC facility, and even if you removed all the servers, to simply try to convert that infrastructure to support DC. It would require an extensive evaluation of all the distribution equipment in there, the wiring, and a lot of other aspects of that facility. So while it's definitely not out of the question, any payback would be highly installation dependent, and chances are a greenfield or a clean facility build out would be a much more efficient way of implementing a DC solution.
Thanks, John. One of the other questions here is, will you be reviewing ABB's specific product offerings for DC distribution in the data centers? And that question should make the marketing folks very happy, because that's one of the major reasons we'd love to have folks come visit us at Automation and Power World. My previous company, Validus, got involved with ABB simply because at the time we were developing our initial products, ABB by far had a vast array of DC product that aligned perfectly with what we needed to manufacture. So ABB has UL listed and IEC approved solutions ranging from what will soon to be released as a 5,000 amp DC breaker all the way down to miniature breakers. So the product lines encompassing that on the insulated case power breaker side of the equation would be the ABB Emax family of breakers, followed by a molded case product line, which is the T-Max, followed by a miniature breaker product line, which is the S800 family of circuit breakers. And all those will be on display in Orlando later this month.
Okay, with that, Katie, I think perhaps we'll turn it back over to you.
Great. Well, thank you so much, Frank and John, for being on today's call. And if anyone didn't get their questions answered, we'll reach out to you and answer those for you. I just want to close today's event with some additional information about APW, which is Automation and Power World. Once again, it's March 25th through 28th in Orlando, Florida. Over 400 hours of training, tons of presenters. Here are some statistics on the powerful training events that we're assembling. We're providing a number of different options for you to register this year. You can register for all three or select one day at a time. They're very reasonable rates. Once again, here's top 10 reasons to attend. And here's the URL for registering for the event. At this URL, you can also find links to conference brochures and additional free webinars just like the ones that you saw today that we're offering in February and March. We look forward to seeing you at the conference. And once again, if you have any questions, just let us know. We appreciate your feedback and comments. When you close the screen, you'll see a short survey that we would love for you to answer. Thank you so much and have a great day.
The organizer has ended this session, and this call will be disconnected. Goodbye.